Assalamualaikum warahmatullahi wabarakatuh. My name is Nurlana Barkis binti Hairi. I will present about the task 1 simulation. Okay, the task 1, we need to analysis the electrical field between the two electrode. Okay, I will generate this electrode by using the FEMM software. Okay, let's try design the problem. Okay, I have done create the problem. Let's try run. Okay, as you can see, this is what we have got after we done design the problem. Okay, we need to find the electric field. Okay, adjust it in here. We will choose the field intensity. Okay, in here we can see the upper bound is the maximum for the field intensity for this problem. Okay, as you can see, this is the highest field intensity in this part. Okay, let's try take a look on the graph. Okay, this is the graph of the field intensity. Okay, that's it from me.
My name is Nashani Vidya Bhalim, AE10045, and I will present about the discussion in task 1. Okay, for discussion on field electromobility, a sphere structure has been applied for a high voltage conductor and ground. And as we know, the outcome of this experiment is electric field that arise from the different air gap size and metal shapes. Okay, we know the two spaceship conductor are each 50 centimeter in diameter and 25 in radius. Okay, to enable an electric spark, we have to occur between the conductor and conductor is considered outflow of two conductor electrode that separated a gap that is frequently. Okay, then we have determined to determine the link between a gap and field stability. The range a gap we increase 1 centimeter until to 70.5 centimeter. Okay, and the result conductor utilization vector is the old design have new value as exposed the new design origin value. Okay, for the conclusion, each point in space is connected electric field when a charge in any form is present. Okay, and in addition, you can see that the conductor shape reflect the electric field intensity since a good conductor shape and design will increase efficiency and make electric field more uniform by increasing the conductor volume of effectively. Okay, that's all from us, and thank you.
My name is Navin. Now I'm going to present about the report for task 2, analysis of force of a gap CI core. The first one is introduction. The finite element method is a numerical technique used to solve complex engineering problems in various fields, including electromagnetics. FEM has proven to be a powerful tool in the analysis and design of electromagnetic device. Finite element method magnetic FEMM is a software package that utilizes the FEM to simulate and analyze magnetic system. FEMM provides a user-friendly interface for the design and analysis of magnetic system. Scope of the lab is to determine the system described in section 2.3.2. Students are required to analyze the force exerted horizontally and vertically. Also, the direction of the force must be determined. Students are expected to show all the simulations result for flux density, field density, current density, and etc. Objective of the lab, the students should understand the concept of electrical field in electrostatic problems. The second one is the student should be able to create the model for finite elements analysis by considering material properties, boundary condition, and mesh generation. The third one and the last one is the student should be able to understand the concept of leakage flux, mutual flux, firing effect, and force exerted in an electromagnetic system. For literature review, creating an air gap can be useful in various situations. Many people and engineers think that increasing a core's maximum flux density handling capacity by adding air in an air gap. Simply said, this is false. The material properties of the core, not an air gap, dictate the maximum flux density of the core. No matter how big the air gap inside a core is, if the maximal flux density is 1.70, it will stay saturated at 1.70. Instead, the air gap significantly increases the core's reluctance. In the area between the two spots, there is a lot of energy that is stored. Flux, this is comparable to an electrical circuit with a high resistance, which requires a greater voltage to push the same current as one with a lower resistance. It is obvious that the root length is remain constant. Thus, it is also reasonable to state that the effect of an air gap is to demand a stronger magnetic field strength for a given flux density than would be the case without the gap.
Hello and Assalamualaikum. I am Muhammad Fazli Bayanan and my matrix number is AE100060. So now I will explain about simulation for task 2. So as you can see, this is the boundary of the design. So if we zoom, you can see that this is the coil and each coil has 500 turn. So this is the material used, which is M50 steel. So we can see the result, see the simulation by clicking this process. So now you can see that our simulation runs perfectly, and you can change the plotted value to show the density plot. So this is it. Okay. So this area means that the flux density is the highest at this area. This is due to the coil that have current density, making the flux density is the highest at this core. So if we change it to field intensity, so you can see that the field intensity is the highest at the air gap between the C core and I core. This is because of the air gap that acts as an obstacle for the magnetic field, making it is the highest magnetic to attract the I core to the C core. So for the next is the current density. So you can see that current density is mostly focused on the coil because the coil has high current density due to the source, which is the Cooper coil with the number of 100 turn that will produce current to magnetize the C core so that the C core can attract the I core. So that's all for simulation task 2. Thank you.
In conclusion, the area where magnetism acts around a magnetic material or a moving electric charge is known as the magnetic field. We can infer from this experiment that the flux density will be higher the narrower the air gap. This is due to the fact that under the old architecture, the stronger the link between the C and I core becomes, the more difficult it is for charge losses. In addition, as seen by the new design for the E and I core, the quantity of coils will also have an impact on the flux density. This is because the flux density brought on by magnetic induction increases the number of coils around the electromagnet.